Okay. Now Kp and Kc are not exactly the same thing. Sometimes they're the same. If you rearrange PV equals nRT and plug that in for Kp and Kc values, you end up with this equation. Okay, the R is the gas law constant in atmospheres, so 0.0821. Temperature is Kelvin, as always. The change in the moles is the moles of the gaseous products minus moles of the gaseous reactants. So products minus reactants, kind of like final minus initial. Okay, so if we want to calculate Kp, we just throw it into this formula and solve for the unknown. So please try that one for this problem. You should get 6.41 times 10 to the negative 3. This problem is worked out in your textbook. It's example number 15.3. Okay, we're going to skip around a little bit just because there are different K values or K types of K values. So Ksp is a solubility product constant. It's a product of the molar concentrations of the constituent ions, each raised to the power of its stoichiometric coefficient in the equilibrium equation. Now, it's a lot of words, but it's the same. It's the same as what we just did with the other equilibrium constant expressions. So I would suggest writing out the equilibrium formulas for each of these, and then you write the equilibrium constant expression. So pause the video and do that. All right, here they are. Okay, so let's give these Ksp values a think here. If we have calcium fluoride with a Ksp value of 4 times 10 to the negative 11, calcium hydroxide is 8 times 10 to the negative 6. Now, if you look over at the solubility rules on the back of your periodic table, it'll say that calcium hydroxide is somewhat soluble. So what that means is it kind of dissolves, kind of doesn't. Okay, so it does have a very small Ksp. Okay, so what that means is in solution, we don't have a lot of these two ions. Okay, the larger the Ksp, the more of these ions you're going to have. Okay, so if we compare these two compounds, which is more soluble? Okay, we can see that the calcium hydroxide has a higher Ksp value, so it is more soluble than the calcium fluoride. Okay, so here's my answer. This is kind of a AP Chem type question. You'll notice that I don't have any the term it in it. We don't want to use that term because it's not specific. I just used it. Anyway, okay, let's just give these two problems a think. What would happen if we raise the temperature of the solution? What would happen if we add more of one of the ions to solution? What would happen in terms of, we want to think the Chatelier's principle. Okay, so if we raise the temperature, we would think that the solubility would increase. Generally, when we raise the temperature of a solution, solubility increases. Okay, if we add more of one of the ions, the solubility would decrease. So if we add more of fluoride ions, the equilibrium would shift. This should be to the left. The equilibrium should shift to the left. Okay, last little bit here on acids and bases. You already read about this last week in your homework, but just want to go over this again. Bronsted-Lowry acids, they're substances that act as a proton donor. The Bronsted-Lowry bases, they act as a proton acceptor. Okay, these go along with conjugate acids and conjugate bases. So a conjugate acid it forms when the base accepts a proton, and the conjugate base gets paired up with the acid. That's when the proton is removed, you get the conjugate base. So there are these pairs that occur in the, especially if we're looking at acid-base reactions, which you looked at last week in your homework. Okay, now the stronger the acid, the weaker its conjugate base. So if we take a look at a very strong acid like HCl, it's going to completely dissociate into hydrogen and chloride. That chloride has no ability to get that hydrogen back. It cannot grab the hydrogen back again to make HCl. So Cl minus is not basic at all. It cannot absorb a proton. Now if we go further down, let's say to hydrofluoric acid is considered to be a weak acid because it doesn't split up in water very well. So the fluoride then is a base because it can grab onto a hydrogen out of the water. So, we're assuming that this is aqueous, so that fluoride can actually grab a hydrogen and rip it off from the water molecule and to make HF, which is its conjugate acid. So fluoride ions are actually considered a base. Okay. So weak acids are the last little bit we're going to look at here. So please write a balanced equation for the dissociation of nitrous acid. Identify the acid and its conjugate base. So please pause the video and do that. Here they are. Okay, so next you're going to write an equilibrium constant expression for this reaction. Here it is. Now that's equal to 4.5 times 10 to the negative 4, and that's something that we would just look up in an appendix of values. Okay. Now if we want to calculate the hydrogen ion concentration for a 0.5 molar solution of nitrous acid, okay, we can use our Ka value. So I'll just go ahead and show you because this is the first time you've seen it, but here's the equilibrium constant expression. Now we don't know what the hydrogen ion or the NO2 ion is going to be. So we're going to set those both as X. We have an equal number of both because each of these is coming from one of these nitrous acid molecules. So that's going to split up in equal amounts. Now we're going to start with a 0.5 molar solution, and some of that is going to dissociate. So we have a minus X here to represent the amount that is going to dissociate into its separate ions. Okay, now we could solve this, like if you move around the variables, you can see that you're going to end up with an x squared on the top. And you'd have to use the quadratic formula to solve for x, but there's a little shortcut. Okay, we can actually ignore the minus x. Okay, very little of the NO2 is going to dissociate because this is a weak acid. And one way we can decide if we're going to ignore the minus x is we can compare the Ka to the molarity of the acid. Okay, the Ka is 3 orders of magnitude smaller. Okay, in other words, 1,000 times smaller than the molarity. So like the molarity was 0.5, the Ka was 4.5 times 10 to the negative 4. So those are very far apart. They're 1,000 times different from each other. Okay, so we can assume that very little of this acid is actually going to dissociate. Okay, so you can try to use a quadratic formula. I put that challenge out to you. It's not that hard. There's actually like super easy little calculators online to do this, but you'll see that the result will essentially be the same. You'll get 2 answers for x. You don't pick the negative one because that doesn't make sense because we're not calculating a negative molarity. So anyway, the positive answer is the correct answer, but you can see that it's almost the same. Pretty much the same as if we ignore that minus x value. So if you just imagine deleting this, solving for x, the 2 x's on the top, you'll end up with 0.015 molar hydrogen ion concentration. Okay. Now if we want to find the pH of this solution, all we do is plug that into the pH formula. Sorry, there's an extra bracket there. Okay, so we end up with a pH of 1.882. Now if we compare this to a strong acid of the same molarity, we would end up with a pH of 0.301 because the strong acid is going to completely dissociate. So we can just throw in the molarity of the acid right there. Okay, now what that means is the strong acid has a lower pH than a weak acid of the same molarity, okay, because a strong acid will completely dissociate where a weak acid does not. So if we compare those 2 molarities, the strong acid is more acidic, it has a lower pH. Okay, I think we did it. Thank you for watching. This will be I know this is 5 pages of notes, but hopefully it didn't take you too long. Okay, the answer to the puzzler was Obi-Wan Kenobi. Hope you have a great week this week. Please see me in the Zoom meeting if you have any questions. Some of you I haven't seen. at all, but totally optional. So have a good one.